Blackbody radiation, complete history and new derivation. Using mechanical illustrations to assist the imagination. James Clerk Maxwell about his model of molecular vortices that helped him to develop an electromagnetic theory. Historical background. Sadi Carnot. In 1824, Sadi Carnot proposed a theory on heat engines, introducing the concept of an invisible and indestructible substance called caloric, widely accepted as heat. According to Carnot, the efficiency of an ideal heat engine is given by this formula, where Tc is the absolute temperature of the cold reservoir, and Th is the absolute temperature of the hot reservoir.
Now let's talk about the Carnot cycle. The Carnot engine is basically the ideal model of a heat engine. It was designed to represent or to obtain the maximum possible efficiency, so it's simply an ideal model. No other engine can have an efficiency that's greater than the Carnot engine, at least as far as we know. But let's draw a PV diagram for this. So we're going to start at position A. In the first step of the Carnot cycle, we have an isothermal expansion. So going from A to B. During this isothermal expansion, heat is added to the system. So we'll call this QH. And the machine, or the engine, performs positive work. Anytime a gas expands, the work done by the gas is positive. Now in the second step, going from B to C, we have an adiabatic expansion. And during an adiabatic process, no heat transfer occurs, so Q is 0. However, since the gas is still expanding, the engine performs positive work during this process. Now, going from C to D, this process is known as an isothermal compression. For any isothermal event, the change in temperature is equal to 0. But going from C to D, heat is released from the engine into the environment. And because the gas is being compressed, the engine performs negative work, which means that the surroundings do work on the engine, so W is negative during this point. It takes effort to compress the gas. You got to put energy into it. And going from D back to A to complete the cycle, that is an adiabatic compression. Q is 0, there's no heat transfer, and because the gas is being compressed, the work performed on it is negative. So that's the Carnot cycle. But there's two equations that you really need to know for this ideal engine. The efficiency of the Carnot engine is 1 minus Tc divided by Th, where Tc is the temperature of the cold reservoir and Th is the temperature of the hot reservoir. And also, the ratio of Qc and Qh is equal to the ratio of Tc and Th.
Rudolf Clausius. Rudolf Clausius reinterpreted Carnot's caloric as entropy, formulating the second law of thermodynamics based on the principle of universal entropy growth. In 1857, Clausius suggested explaining heat in terms of molecular motion. The Carnot efficiency can be expressed as the ratio of the work output W to the heat input QH from the hot reservoir. Using conservation of energy, we have W equals QH minus QC. Substitute into the efficiency formula. The efficiency equals 1 minus QC over QH. Using Carnot efficiency formula, we find QH over TH equals QC over TC. From the relation obtained for reversible processes, Clausius introduced the concept of entropy. He defined it as the ratio between the infinitesimal amount of reversible heat and the absolute temperature. In other words, the change in entropy equals the reversible heat divided by the temperature.
Given a difference in temperature, a high temperature, T sub I, and a low temperature, T sub O, Carnot designed a perfect abstraction. The Carnot engine takes in heat, Q sub I, at the high temperature, turns some of it into work, W, and expels the rest, Q sub O, as heat at the lower temperature.
Because the Carnot cycle could run just as well in reverse, it was the picture of the ideal engine, the most efficient machine the laws of nature could possibly permit. In Carnot's ideal engine, the ratio of the heat taken in to the heat wasted was the same as the ratio of the two absolute temperatures needed to drive the engine. In other words, and this was the ideal that stemmed from Carnot's imagination, something that goes in is the same when it comes out. If it's not the heat, and if it's not the temperature, what is it? It's the heat divided by the temperature at which it flows. And according to Clausius, that's entropy. In a Carnot engine, some entropy flows in at high temperature, does its job, and the same amount of entropy flows out at low temperature. So an ideal engine not only conserves energy, it conserves entropy as well. That's the ideal. But what about the reality? In the real world, with the clanking, hissing, whistling, puffing engine, what really happens? For one thing, all engines conserve energy. The work equals the difference between the heat in and the heat left over. But using the same temperatures, a real engine does much less work than Carnot's ideal. It does less work and leaves more heat to release. So even though the entropy that flows in might be the same as Carnot's, the entropy that flows out is bigger. That's an amazing fact. The entropy that flows out of a real engine is bigger than the entropy that flows in. And when a body finally has the same temperature as its surroundings, it's in a state of equilibrium. As long as heat flows, as long as a warm body is warmer than the cool one, entropy will increase. And it will continue to increase until nothing else can possibly happen. The state of equilibrium, and should that happen, entropy would increase no more. In other words, the state of equilibrium is the state of maximum entropy.
Entropy, together with energy, is probably the most vital concept in nature. Energy remains constant. Entropy, instead, increases continuously. It can never decrease. This is exactly the essence on which the second law of thermodynamics is based. The entropy of a system of bodies may only increase. When brought to its maximum levels, it remains constant. If it increases, then the process is irreversible. If it remains constant, it is reversible and may even be inverted. This is the major difference between the laws of nature. Thermodynamical equilibrium occurs when entropy has reached its maximum level. If it does not increase, then no change can occur either.
James Clerk Maxwell. Building on Clausius's work on the molecular model of heat, James Clerk Maxwell developed a theory of molecular collisions and derived a mathematical expression for the distribution of gas molecule velocities. Let's start by considering a gas made of many molecules moving randomly in space. Maxwell assumed that the probability of a molecule having a certain velocity depends only on the speed, not the direction. This leads us to a probability function separable in each Cartesian component. Because the gas is isotropic, each direction behaves the same. Maxwell also assumed the distribution is Gaussian, so, similarly for Vy and Vz, the full 3D distribution becomes: to find A, we normalize over all velocities. Finally, to express the distribution as a function of speed v, we switch to spherical coordinates and include the volume element. This is the Maxwell speed distribution, describing the probability of finding a gas molecule with speed v at temperature T. Ludwig Boltzmann. Between 1868 and 1871, Ludwig Boltzmann extended Maxwell's velocity distribution by expressing it in terms of energy rather than speed. This led to the formulation of the Maxwell-Boltzmann distribution. Boltzmann introduced a statistical method to calculate all possible microscopic states of a system by accounting for all combinations in which energy can be distributed among molecules. This framework allowed him to interpret entropy as a measure of the number of such possible configurations, linking thermodynamics with molecular behavior. This insight led him to formulate the now famous equation, S equals K times the natural logarithm of omega, where S is the entropy. K is Boltzmann's constant, and omega is the number of possible microstates, or ways the total energy can be distributed among the molecules.
Take a statistical look at the idea of entropy. One of the best ways to do this is to imagine the dispersal of energy occurring from molecules actually dispersing into space. And that's fairly easy to envision for gas particles because we have a nice small particle model for gases. So let's start off imagining a situation where we have a box, and the box is divided into two sides, a left-hand side and a right-hand side, and we'll imagine there's only one gas particle in the box. And so we'll say there's one little particle, and the key idea is that this particle is in motion, and it's important to remember that for all molecular pictures that we have of matter, the particles are always in motion. They're either vibrating or moving around. Even atoms and solids can be translating even if it's on very, very long time scales. So these molecules aren't fixed in space, but they can move. And so we want to ask a basic question, which is, where will we find the gas in the box? Is it going to be on the left-hand side of the particle, or the left-hand side of the box, or the right-hand side of the box? So since the particle is moving around, it's just exploring all possible spaces. And what we want to look at are snapshots in time. So these aren't fixed positions, but this is what any configuration might look like if we just took a snapshot in time. So one chance is that the particle is on the right-hand side of the box, and we can imagine that if we let it move around and we took a bunch of snapshots, a good fraction of the time, in fact exactly half of the time, we would discover the particle on the left-hand side of the box. And so with only one particle, these two are equally likely. That is, there's no reason to believe there'll be any difference between one particle on the left or one particle on the right. And so here we have a situation where we know, if we wanted to know where is the particle, well, it's exploring the entire box. What happens though if we move on to two particles? If we have two particles, we now have two particles in the box and they're moving at the same time. And so we can imagine them starting on the left, and then if they move around and then we take a snapshot, we might capture them both on the left. But if they're moving around and we're taking snapshots in time, we know that there's some chance that we'll find one on the right and one on the left. Or alternatively, they might switch places and the first particle might be on the left and the second particle might be on the right. Or we might, in some snapshot in time, find them both on the right. Now, these possibilities are no longer equal to one another. And the reason they're no longer equal is that the particles don't have labels. We don't know which one is number one and which one is number two. And for that reason, these two here in the middle are actually the same configuration. That is, we would call them equivalent. And so if we looked at all possibilities and we said, what are the chances the particles are both on the left-hand side, or what are the chances the particles are both on the right-hand side, or what are the chances that there's one on each side? It is more likely that there's one on each side because there's two equivalent ways to achieve that. Particle 1 can be on the left and particle 2 on the right, or 2 on the left and 1 on the right. As we increase the number of particles, we'll see that we get an ever-increasing number of equivalent states for different configurations. So let's look at what happens when we have 4 particles. If we have 4 particles, we now have to imagine there's some possibility that they could all show up on the left-hand side, but there's also a chance that one of them is on the right. And in fact, we know there's several ways to make this configuration. We could have the first particle there, or the second particle there, or the third particle there, or the fourth particle there. So we have 4 different ways to achieve that configuration with 3 on the left and 1 on the right. Could be that there's 2 on each side. It could be that there's more particles over on the right-hand side. What we want to do now is to count up the different ways that we can arrange the particles and arrive at these equivalent configurations. So for that first one, we know there's only one way to do that. All of the particles have to be on the left. We call this number of ways of achieving this configuration, we give it a symbol omega. This is the number of equivalent microstates. So these pictures that we're taking are microscopic states of the system. Where is the energy? How is it distributed? Where are the particles? How are they distributed? So for the first one, there's only one way to do that. All of the particles have to be on the left. But as I pointed out, for the second one, there's 4 ways to do that, because any one of the 4 particles could be the one on the right, and since they don't have numbers or letters on them, they're all exactly the same, then there have to be 4 equivalent ways to do that. Turns out that for the middle, with the 50-50, there's 6 equivalent ways, and then for 1 on the left, there's 4 again, and all of them on the right, there's 1 again. So you can see now it's becoming ever more likely for us to be getting to this equally distributed. That is the highest probability. So if the particles do whatever they want, and we just take a snapshot at a moment in time, the most likely picture that we get is this one here in the middle, because there are 6 different ways that we could arrive at that picture. However, it could be one of these other 2. Those are equally likely, but these extremes are unlikely because they're very special microstates. And so we see that the chances of them is decreasing rapidly. If we move up now to 10 particles, now we can see that the 50-50 states here, where we have 5 on the left and 5 on the right, are becoming incredibly likely. There is 252 equivalent ways to make this state, whereas everybody on one side or the other is highly unlikely. And in fact, only 1 on one side or 2 on one side is very unlikely. So now, what are the chances that we find things equally distributed? They're very, very high. What if we don't have 1 or 2 or 4 or 10 particles, but we have Avogadro's number of particles? If we have Avogadro's number of particles, it's extremely likely that we will get equally distributed particles, because every particle on the left or every particle on the right has so small a chance of occurring that we can say it never happens. What will happen? Let the particles go wherever they want. Imagine a snapshot in time. They are going to be spread out 50-50 on each side of the box. What is forcing them to do this? Nothing. The particles simply move where they would like to move, and the equally distributed case is simply statistically the most probable case. Does it have to be exactly 50-50? Half Avogadro's number on one side and half on the other? No. We can get some small fluctuations, but we never get these immense fluctuations where we see all the particles on one side and all the particles on the other. This number of equivalent microstates is a measure of the entropy. So this idea was formulated by Boltzmann, who said the entropy was equivalent to some proportionality constant, this is the Boltzmann constant, times the natural log of the number of equivalent microstates, omega. So if we have more volume in a system, there's more ways to arrange our particles. That makes for more microstates and more entropy. It's important to realize that these microstates are not just for arranging positions of molecules, but also how energy is distributed within the molecules and between the molecules. And so higher temperature will be more energy to distribute, more energy will be more microstates will be more energy. Also, if we have more molecules in the system, more molecules means more microstates means more entropy. And so all of these ideas play out, that it is the number of equivalent microstates that we have, which is why some situations are higher in entropy. So let's look at a spontaneous change. Now let's imagine that we have our gas and it's confined to the left-hand side of our box because we put a wall there. And so it can't go anywhere. And so this starts at a lower entropy configuration because there are fewer equivalent microstates for that situation. But if I remove the wall now, I know what's going to happen is the gas will spread out because it's just randomly moving around. How will it end up? Most likely it will end up spread out 50-50. And that's because in the 50-50 configuration we have many equivalent microstates. So we go from a situation with few microstates, much lower entropy, to a situation with many microstates, much higher entropy. And this is the reason that we move from low entropy to high entropy. We're going from configurations which are less likely to occur to the configurations which are most likely to occur.
Josef Stefan. Since the 18th century, it was understood that heat transfer between bodies does not increase linearly with temperature difference. In 1879, Josef Stefan, based on experimental measurements, proposed that the total radiated energy from a hot surface is proportional to the fourth power of its absolute temperature. This empirical law was later derived theoretically by Boltzmann in 1884, by modeling electromagnetic radiation as the working fluid in a Carnot cycle. Physicists became increasingly fascinated by the fundamental nature of electromagnetic radiation and its relationship to energy, especially in understanding how energy is distributed across frequencies in blackbody radiation. Gustav Robert Kirchhoff introduced the concept of a blackbody in 1859, describing it as an ideal object that absorbs all incoming radiation. This idea became a cornerstone in the study of thermal radiation. Wilhelm Wien. After analyzing experimental data from blackbody ovens, Wilhelm Wien proposed a law stating that the wavelength corresponding to maximum radiation emission is inversely proportional to temperature, such that the product of wavelength and temperature remains constant. This principle became known as Wien's displacement law, which he derived by envisioning an expanding and contracting cavity filled with radiation. Subsequently, he combined his displacement law with the Stefan-Boltzmann T to the fourth power law to derive a blackbody spectrum. Max Planck expanded upon Wien's model by applying Boltzmann's statistical methods and the concept of entropy. However, he reluctantly introduced the idea that the energy of radiation must be distributed in discrete amounts among individual modes of vibration. This quantization of energy marked the foundational step toward the development of quantum mechanics. The actual historical account shows that Planck initially derived Wien's radiation law using thermodynamic arguments based on entropy. When experimental results later revealed that Wien's formula failed to match observed data at low frequencies, Planck turned to Boltzmann's statistical methods to derive a new radiation law. In doing so, he reluctantly interpreted the term HF as representing quantized energy. Contrary to the commonly told yet inaccurate story, Planck was not attempting to solve the so-called ultraviolet catastrophe. That interpretation emerged later with the work of Rayleigh and Jeans. Now, we're going to explore how Wien's displacement law, Wien's radiation law, and Planck's law were originally derived step by step and in detail. The following derivations are taken directly from a video by Sander Koneinenberg. Full credit to him for the original content. You'll find the link in the description below.
To reiterate, even though we call it a photon gas, these derivations are fully classical and make no assumptions of photons, which weren't introduced until the development of quantum theory. We now know how the total radiation energy is related to temperature. However, we saw that for different temperatures, the radiation intensity follows different functions of radiation frequency, in the same way that the molecular velocities follow different distributions for different temperatures. We want to understand what these functions look like exactly. The first step to understanding this is Wien's displacement law. Wien's displacement law states how the frequency, which has maximum intensity, changes with temperature. The derivation of Wien's displacement law consists of the following steps. We consider a container where one of the walls slowly moves inward with a small velocity v, and we see how this will affect the radiation inside it. One thing it does is that it changes the frequency of the reflected radiation due to the Doppler effect. So if light with a certain frequency hits the wall at a certain angle, then depending on the angle and the velocity of the wall, the reflected light will have a different frequency. Moreover, because the wall is moving, it transfers energy to the reflected radiation. This means that the reflected light will have a higher intensity than the incident light. Taking these two effects into account, we can calculate how much light will be leaving the frequency interval f plus df after reflection from the moving wall. So if diffuse light within a certain frequency interval hits the moving wall from all different angles, the reflected light will have left that frequency interval due to the Doppler shift. Furthermore, we can calculate how much light enters the frequency interval f plus df due to reflection from the moving wall. If light with certain frequencies hit the moving wall at certain angles of incidence, the reflected light will have a frequency inside the interval f plus df. Once we know how much light leaves the interval and how much light enters the interval, we can take the difference to find the net energy change in that frequency interval. This will yield a differential equation that relates the frequency content of the light to the volume of the box, which changes due to the moving wall. If we assume that the compression is quasi-static, then the system always remains in equilibrium as we're moving the wall, which means the temperature of the radiation always remains well defined. What we will end up with is a formula that gives the energy of light with a certain frequency f if the radiation has a certain temperature T. The derivation will follow the lecture notes by Max Planck on the theory of heat radiation. So let's go through the 4 steps of the derivation, starting with the Doppler shift. The Doppler shift occurs due to 2 boundary conditions, namely that the incident and reflected fields must be the same at the wall, or have a fixed phase shift, and both the incident and reflected fields propagate with the same speed of light c. For simplicity, let's first consider a field at normal incidence. The incident field propagates in the x direction. Upon reflection, the propagation direction switches sign, and the wavelength and frequency can change. Both fields propagate at the speed of light c. The surface at which the 2 fields must have the same value is the wall, which moves in the negative x direction with speed v. We can write down the condition for continuity. Then we fill in the value for x at which continuity must hold. We divide both sides of the equation by k. We use the expressions for the speed of light c to rewrite both sides of the equation. By solving for the ratio of angular frequencies, we find by how much the frequency of light changes upon reflection. Because the wall is moving much more slowly than the speed of light, we can Taylor expand the expression around v equals 0. Now let's see how the Doppler shift depends on the angle of incidence. The incident field propagates in the xz plane. The reflected field also propagates in the xz plane, but because of the reflection, the x component of the propagation direction switches sign. We can write down the equation for continuity, and we can specify that continuity should hold at the wall where the light reflects. We can collect the terms that contain the time t and the terms that contain the position z. Because this equation must hold for any arbitrary z and t, both prefactors must be 0. Now let's define the incident angle theta and the angle of reflection theta prime. The x component of the k vector depends on the cosine of the angle, and the z component depends on the sine of the angle. The same holds for the reflected field. We can use these expressions to rewrite the two equations in terms of theta and theta prime. We can rewrite the first equation using the expression for the speed of light c. We then find the shift in frequency due to reflection from a moving wall. However, this expression involves both theta and theta prime, and we don't know yet the relation between them. For that, we use the second equation, which we can rewrite using the fact that the ratio between frequencies is the same as the ratio between wavelengths. We end up with the following two equations that describe the Doppler shift. To simplify it, we assume that the speed of the wall v is much smaller than the speed of light c. In this limit, the angle of incidence is equal to the angle of reflection, and we can Taylor expand the expression for the Doppler shift around v equals 0. We note down this final result for future reference. Now we will examine how the intensity of light is changed due to reflection from a moving wall. We saw that if light hits the wall at an angle theta, the force it exerts is reduced by a factor cosine theta. The force is given by the radiation pressure times the area of the wall. If the wall moves with a velocity v, it performs an amount of work equal to the force of the radiation times the distance that the wall moves. This work is transferred to the reflected light. So the energy of the reflected ray per unit area is given by the energy of the incident ray plus the force of the incident light times the distance that the wall moves. Dividing both sides by dt and collecting terms gives us the final expression that relates the intensity of the reflected light to the intensity of the incident light. We also note down this final result for future reference. Now we will calculate the amount of radiation energy that leaves the frequency interval f plus df due to reflection from a moving wall. Basically, any radiation within the frequency interval that gets reflected by the moving wall will leave that frequency interval due to the Doppler shift. So to calculate the total radiation energy leaving the frequency interval, we simply calculate all the energy that hits the wall with area A within a time dt. Recall that for diffuse light, the intensity of light is the same in all propagation directions, so it can be taken outside the integral. Now we will calculate the radiation energy that enters the frequency interval f plus df due to reflection from the moving wall. Suppose the incident radiation lies in some frequency interval f prime plus df prime. Due to the Doppler shift, it gets shifted to another interval. The initial interval f prime plus df prime should be such that the radiation gets shifted into the interval f plus df. Recall that as the radiation gets reflected by the moving wall, not only the frequency shifts, but also the intensity. So if the incident radiation has intensity IF prime inside the frequency interval df prime, the intensity gets shifted upon reflection by some factor. We see that if we multiply this factor with the initial frequency interval df prime, we obtain the final frequency interval df. So the intensity that enters the interval f plus df we call IF df, and it is equal to IF prime df, where f prime is such that when it gets Doppler shifted, it becomes f. In the limit of small velocities v, this frequency is f times 1 minus 2v cosine theta over c. Assuming the Doppler shift is small, we can Taylor expand the intensity as function of frequency. To calculate the total energy entering the frequency interval f plus df, we integrate the intensities that will end up in that interval over all angles. Recall that for diffuse light, the intensity is the same in all propagation directions, so this can be taken as a constant outside the integral. Now that we have calculated the radiation energy that enters the frequency interval and that leaves the interval, we can calculate the net change in energy due to reflection from a moving wall. We take the two expressions for the outgoing and ingoing energy that we found previously, and then we take the difference. We see that the difference consists only of the term containing the derivative of intensity with respect to frequency. While deriving the Stefan-Boltzmann law, we derived an expression relating the intensity of the radiation to the energy, and we defined the energy density as energy divided by volume. With these two definitions, we can write the energy difference in terms of the energy density. Note that if the wall with an area A moves at velocity v for a time dt, the volume of the box decreases by A times v times dt. We use this result to rewrite the change in time as a change in volume. Furthermore, we can write the difference in energy in terms of a difference in energy density and a difference in volume using the product rule. We equate this to the expression we found previously. We can rewrite this as an equation involving the derivatives of energy density with respect to volume and frequency. By substitution, we can verify that this equation is solved when the energy density for a certain radiation frequency is equal to the third power of frequency times an arbitrary function f of the third power of frequency times the volume of the box. So we have found an expression for the energy density of radiation as a function of frequency. However, our goal is to relate this to the temperature of radiation, and so far, there is no reference to temperature. To introduce temperature in this equation, we recall the expression that we found for the entropy of a photon gas. If we assume that the photon gas is compressed adiabatically and quasi-statically, then the temperature is always well defined, and the entropy remains constant during the compression. Therefore, we can write the volume as some constant divided by the third power of temperature. If we plug this into the expression for the radiation energy density as function of frequency, we find that it depends on a function f of frequency divided by temperature to the third power. Or equivalently, we can write it as some other function f prime of frequency divided by temperature. With this expression, we can now derive Wien's displacement law, which tells us at which frequency the energy density is maximal for a given temperature. Let's call the frequency divided by temperature x. To find the frequency for which the energy density is maximal, we take the derivative of the energy density with respect to frequency and set it equal to 0. We can calculate the derivative using the product rule and the chain rule. When we set it equal to 0, we can divide out the frequency squared and find that we have an equation that depends on x only. Let's say that this equation is solved for a certain value of x, called x0. Then, for any given temperature T, the frequency f0, for which the energy density is maximal, is such that f0 divided by T equals the constant value of x0, and this is precisely Wien's displacement law. So now we understand Wien's displacement law, which tells us for which frequency the energy distribution is maximal at a given temperature. But Wien went one step further and wanted to determine the shape of the entire distribution, not just the location of its maximum. To come up with the formula for the energy distribution of blackbody radiation, he used the following line of reasoning. It was known that an accelerating charge generates electromagnetic radiation, so the frequency of the radiation that is emitted is probably somehow related to the velocities of the molecules. So similarly, the molecules' velocities can be written as some function of the emitted frequency. From statistical mechanics, we know that the molecule's velocities follow the Maxwell-Boltzmann distribution. This distribution contains 1 divided by temperature in the exponent. We previously derived that the energy density is a function of frequency divided by temperature. So we can infer that the expression for the energy density contains the exponential of frequency divided by temperature. Based on the formula we derived previously, it should also contain a factor of the third power of frequency. To find the total energy density, we can integrate over all frequencies, and we find that it is proportional to the fourth power of temperature, as it should be according to the Stefan-Boltzmann law. In fact, Wien originally inferred that there should be a factor of frequency to the third power in order to enforce a match with the Stefan-Boltzmann law. We can also choose to write the distribution in terms of wavelength instead of frequency. We know that frequency equals the speed of light divided by wavelength, so the derivative of frequency with respect to wavelength is proportional to 1 divided by the wavelength squared. Therefore, the distribution as we found it is proportional to 1 over the fifth power of wavelength. The radiation law that Wien derived matched well with the experimental data that was available at the time, and it had some sort of physical justification. However, Max Planck didn't like this derivation because it used the Maxwell-Boltzmann distribution, which is based on statistical mechanics and kinetic theory. At the time, Boltzmann's statistical mechanics and his statistical interpretation of entropy was not yet widely accepted. Clausius introduced entropy to quantify the degree to which a system has spontaneously and irreversibly transformed. For example, as heat spontaneously flows from a hot body to a cold body, the entropy of the complete system increases. Therefore, it was seen as a fundamental law of nature that entropy in a closed system should always increase. However, in Boltzmann's interpretation, increase of entropy is merely a matter of probability. For example, consider a container with 2 connected compartments A and B. Molecules are moving around randomly, so due to diffusion, after some time the system settles in a state of maximum entropy, where approximately equal amounts of molecules occupy compartment A and compartment B. But now let's introduce a little demon between the compartments. If a randomly moving molecule happens to go from A to B, the demon lets the molecule pass. But if a randomly moving molecule happens to move from B to A, the demon blocks it, so that the molecules stay in compartment B. What will happen now is that due to random movement of the molecules and just a little bit of intervention from the demon, all molecules will end up in compartment B. The gas has undiffused, and its entropy has decreased. Another objection to explaining the irreversible increase of entropy using molecules that obey reversible laws of motion is Loschmidt's paradox. Suppose you have some molecules that move in such a way that the entropy of the system increases in time. Now let's consider the same configuration of molecules, except the directions of the velocities are exactly reversed. Then the entropy of the system decreases in time. So for each configuration where entropy increases, there is a configuration where entropy decreases. So entropy should either increase or decrease with equal probability. Planck's objection was the following. If we know nothing in advance about the state of the system, then we can speak about it in terms of probability. However, if we know the state of the system, then its evolution is determined by the laws of mechanics, not probability. So we cannot say that improbable states evolve to probable states, which in Boltzmann's interpretation means evolving from low entropy states to high entropy states. We can only say that an initial state, however probable or improbable, evolves according to the laws of mechanics. For this reason, Planck was unsatisfied with the physical justification for Wien's law, which was based on molecular kinetics and the Maxwell-Boltzmann distribution. He wanted to derive the same law, but from different physical principles, namely the theory of electromagnetism and the principle of increase of entropy, which he regarded as a fundamental law that cannot be derived using Boltzmann's statistical mechanics. Instead, he proposed the following picture. From the work of Heinrich Hertz, Planck knew that oscillating charges emit electromagnetic radiation, so he imagined the presence of some sort of oscillators that emit and absorb electromagnetic radiation. He wasn't sure what these oscillators are precisely, but they should have some connection with the actual atoms of the radiating matter. When the charges oscillate, they emit radiation, and conversely, incident radiation will stimulate the charges to oscillate. Planck's goal was to find an expression for the entropy of the oscillators and the electromagnetic radiation. If we also know the energy of the oscillators and the radiation, we can determine the temperature of the oscillators and the radiation using the derivative of entropy with respect to energy. This relation is then used to derive Wien's law, although what we're of course actually doing in practice is using the already known Wien's law to find the expression for entropy, and then use that expression as the physical foundation of the theory. When coming up with an expression for the entropy, Planck made the following considerations. We expect the expression for entropy to be similar to the one that was known from the thermodynamics of gases. When the system is in equilibrium, the entropy should be maximal, and it should correspond to the state where radiation is emitted and absorbed at equal rates. So let's find an expression for the entropy of the oscillator, starting from Wien's law. Wien's law states that in equilibrium, the intensity of electromagnetic radiation that is emitted at a certain frequency and temperature is proportional to the third power of frequency times an exponential that depends on frequency divided by temperature. If an oscillator vibrates at a frequency f and has energy UF, then one can verify through dimensional analysis that the emitted intensity is the oscillator energy times the frequency squared divided by the speed of light squared. Since we know the intensity from Wien's law, we can infer that the oscillator's energy is proportional to frequency times an exponential that depends on frequency divided by temperature. To infer the oscillator's entropy from this, we use the fact that 1 divided by the temperature equals the derivative of entropy with respect to energy. We use the expression for the oscillator's energy to find the expression for 1 divided by the temperature in terms of the oscillator's energy. If we integrate this expression with respect to energy, we find the entropy of the oscillator. In an attempt to justify this formula for the entropy of an oscillator on more fundamental grounds, Planck analyzed the entropy change of an oscillator absorbing energy from a stationary radiation field. He came to the conclusion that the fundamental starting point for deriving Wien's law should be the assumption that the second derivative of the entropy of the oscillator with respect to its energy should be proportional to 1 divided by the frequency times the energy. So Planck tried to derive Wien's radiation law from electromagnetism and the principle of increasing entropy, whereas Wien's starting point was the Maxwell-Boltzmann distribution from molecular kinetics. But then, new experimental data came in that contradicted Wien's radiation law. It turned out that for small values of frequency over temperature, Wien's radiation law failed to match the experimental observations. So Wien's law fails at high temperatures or long wavelengths, such as deep infrared radiation. How did Wien and Planck respond to this news? Since Wien's starting point was molecular kinetics, he simply argued that at high temperatures, the molecules must somehow move differently. Planck, on the other hand, found this contradiction much more problematic for his approach, and he felt much more urged to address the issue. In retrospect, Planck commented that because he focused on the question of entropy, he could make progress that other physicists couldn't. So let's see how Planck solved the mismatch between his theory and experiments. Recall that Planck's starting point to derive Wien's law was that the second derivative of an oscillator's entropy with respect to its energy should be proportional to 1 divided by the frequency times energy. The resulting Wien's law is valid for large values of frequency divided by temperature. However, for small values of frequency divided by temperature, experimental observations indicate that the radiation intensity is directly proportional to the temperature. The radiation intensity is directly proportional to the oscillator energy, so the oscillator energy is given by some constant times the temperature. Using the relation that 1 divided by temperature equals the derivative of entropy with respect to energy, we find that the entropy of the oscillator should be proportional to the logarithm of its energy. The second derivative of the entropy with respect to energy is therefore proportional to 1 divided by the energy squared. So now we have two expressions for the second derivative of entropy with respect to energy, which should be valid for different limits of frequency divided by temperature. Combining the two expressions, we find a new result that reduces to the original two expressions in the two limits for frequency divided by temperature. So what will be the new radiation law that follows from this expression for the second derivative of the entropy of an oscillator? If we integrate the result with respect to energy once, we should get an expression for 1 divided by the temperature. So let's integrate with respect to energy. Now we can solve for the energy. This result describes how the energy of the oscillator depends on frequency and temperature. To calculate the radiation intensity that such an oscillator generates, we multiply the energy with the frequency squared divided by the speed of light squared. This yields a new radiation law, which turned out to match with the experimental data perfectly. But what is the physical interpretation of this new law? So far, we just changed the second derivative of entropy to make it fit the data, but there was no physical justification for doing this. To physically interpret this new result, let's calculate the entropy of an oscillator according to the new formula we found. To find the entropy of the oscillator, we solve for 1 divided by temperature using the expression for the energy. This, by definition, is equal to the derivative of the oscillator's entropy with respect to its energy. So we integrate with respect to energy to find the entropy of the oscillator. To give this expression for entropy a physical interpretation, Planck turned to Boltzmann's statistical mechanics. Recall that initially, Planck opposed Boltzmann's methods, because he believed they couldn't properly explain the increase in entropy as the second law of thermodynamics required. However, because Planck saw no other way to give a physical explanation for his radiation law that matched the experimental data so well, he nonetheless accepted Boltzmann's approach. So consider the following situation. We distribute n distinguishable packets of energy over n distinguishable oscillators. We saw in a previous video how we can compute the number of ways in which this can be done, and that we can apply Stirling's approximation to simplify this expression. For large numbers of energy packets and oscillators, the multiplicity of the most likely macro state is practically equal to the total number of ways the energy packets can be distributed. We can calculate the entropy of the total system of n oscillators by using Boltzmann's definition of entropy. We can plug in the expression that we found using Stirling's approximation. We can rewrite it so that it more closely resembles the expression that we're trying to explain. The average energy per oscillator is given by the total energy divided by the number of molecules. Therefore, we can write the number of energy packets m divided by the number of oscillators n in terms of the average oscillator energy. We can plug this into our expression for the total entropy of n oscillators to find an expression for the average entropy of a single oscillator. By comparing this to the expression for entropy that we found from Planck's radiation law, we can now interpret the meaning of the constants A and B. A times the frequency gives the energy of a single energy packet, and B equals A divided by Boltzmann's constant. If we substitute this into the expression for the oscillator energy, we find the term e to the power energy divided by Boltzmann's constant times temperature. This should remind us of Boltzmann factors, which we saw in a previous video. Indeed, a modern derivation of Planck's law typically uses Boltzmann factors. In this derivation, we start with the assumption that the energy levels are equally spaced with some finite interval epsilon. If the oscillator is in thermal equilibrium with an environment of temperature T, then the probability to be in a certain energy state is proportional to the Boltzmann factor, where we can plug in the expression for the energy levels. we can calculate the normalization constant or partition function by summing all Boltzmann factors. After plugging in the expression for the energy levels, we can use the formula for calculating a geometric sum to find an expression for the partition function. We know from a previous video that the average energy of a system is found by taking the derivative of the logarithm of the partition function with respect to the thermodynamic beta. Performing this calculation and simplifying this expression yields Planck's formula for the average energy of an oscillator. And if we know the energy of an oscillator, then we saw that we can calculate the radiated intensity by multiplying with the frequency squared divided by the speed of light squared. And we saw that we can calculate the energy density by multiplying the radiated intensity with 4 pi divided by the speed of light. Plugging in the expression for the radiated intensity and the energy of an oscillator, we find a final expression for the energy density of radiation of a certain frequency. However, throughout all the derivations that we performed, we ignored the 2 degrees of freedom due to the polarization of light. So the final result is multiplied by a factor of 2. Now that we got an impression of how Planck came up with his radiation law, let's make some remarks about the historical sequence of events. Some sources on this topic may mention the Rayleigh-Jeans radiation law and the ultraviolet catastrophe as the motivation for finding Planck's radiation law. The storyline goes as follows. We saw in a previous video that for a molecular gas, the equipartition theorem states that the total internal energy is equally distributed over all degrees of freedom. Then, according to classical theory, we can apply the same equipartition theorem to radiation. That is, all the radiation energy is equally distributed over all modes of radiation. Here, every frequency and propagation direction of radiation corresponds to a different mode. If we assume the density of modes is constant in frequency space, then the number of modes around a certain frequency f is proportional to f squared, because all the different possible propagation directions cover the area of a sphere with radius f. So the higher the radiation frequency, the more modes there are, without any upper limit. According to the equipartition theorem, all modes contain the same amount of energy. These 2 observations together lead to the conclusion that the energy must diverge for higher frequencies at any given temperature, which is obviously unphysical. It would imply that a blackbody at a certain temperature would radiate an infinite amount of energy and at arbitrarily high frequencies. Since ultraviolet light has a higher frequency than visible light, this unphysical divergence is called the ultraviolet catastrophe. As the story goes, the quantization hypothesis was introduced to solve this ultraviolet catastrophe. The reason why quantization would solve the ultraviolet catastrophe is this. According to the logic behind the Rayleigh-Jeans law, there are more modes with higher frequency, and if all modes should contain the same amount of energy, then more energy is put in radiation with higher frequency. If we introduce the concept of quantization, then still higher frequencies have more modes. But these modes are more difficult to excite, because the energy should exceed a threshold that becomes higher for higher frequencies. For very high frequencies, that threshold is higher than the total energy of the system, so these cannot be excited at all. This trade-off between the number of modes and how easily each mode can be excited leads to the typical curve that goes to 0 for very low frequencies and very high frequencies, and has a maximum in between. However, this storyline involving the ultraviolet catastrophe is different from the storyline we discussed previously, which involved Wien's radiation law and Planck's argumentation from entropy. This discrepancy between the actual historical sequence of events and the popularized quasi-history of the ultraviolet catastrophe has been the subject of several commentaries. At this point, one might wonder, how important is this historical accuracy anyways? Surely what's truly important is that we properly understand the correct physics, right? However, if at some point you want to take part in making scientific progress, it may be helpful to know what making progress realistically looks like. The problem with quasi-history is that it presents an unrealistic picture of the discovery of new scientific concepts. Either the development appears so obvious that it is trivial, or the discoverer had an inexplicable stroke of genius. In the case of Planck's radiation law, the quasi-history makes it seem as if Planck solved the ultraviolet catastrophe with a single brilliant insight. But that ignores the careful and lengthy examination of different views that was necessary to reach the solution. It downplays the degree to which Planck relied on the work of others, and the fact that Planck had to change his opinion on the statistical ideas of Boltzmann. So let's summarize the differences between the quasi-history and the real history behind the development of Planck's radiation law. The first point on which the two histories differ is what the best radiation law was before Planck's law. According to the quasi-history, it was the Rayleigh-Jeans law, which suffered from the divergence for high frequencies. However, we saw that actually it was Wien's radiation law. It is interesting to note that the Rayleigh-Jeans law wasn't introduced until years after Planck's law. One might wonder why a wrong law would be proposed after the correct law was already proposed years ago. But such is the reality of scientific progress. It doesn't necessarily follow a linear logical structure, but rather it can take quite some time before a correct idea is properly understood and accepted, in the same way that it took time before Planck accepted Boltzmann's statistical ideas. The second point where quasi-history and real history differ is for which wavelength regime there was a mismatch between experiment and theory. According to quasi-history, the mismatch was in the ultraviolet regime, where the theory predicted a divergence in energy, whereas in practice no such thing is observed. However, what actually happened was that the prediction of Wien's law failed in the infrared regime. The third point where the quasi-history differs from the actual history is the way in which the mismatch was solved. According to quasi-history, Planck simply assumed that the energy levels of an oscillator are quantized, and with that assumption, the correct radiation law follows straightforwardly. However, what actually happened is that Planck assumed that the second derivative of the oscillator's entropy with respect to its energy should have a certain form. From that he calculated the radiation law and the expression for the entropy of an oscillator. He then reluctantly turned to Boltzmann's statistical mechanics to give this expression a physical interpretation. Now let's summarize what we've seen in the past few videos. We started with the steam engine. Its invention had a major impact on society during the Industrial Revolution, which motivated scientific research on this topic. Sadi made the following two observations. First, the steam engine can be abstractly represented as a heat engine. Heat flow is used to perform mechanical work. Second, the most efficient heat engine is one that is reversible. Clausius took these observations and elaborated on them further. Firstly, he identified that internal energy, heat, and mechanical work are different forms of energy, which can be transformed into one another, while the total amount of energy remains conserved. This is the first law of thermodynamics. Secondly, he quantified the degree to which a system has irreversibly transformed by introducing the concept of entropy. The second law of thermodynamics states that in a closed system, entropy can never decrease. Then came the development of kinetic theory and statistical mechanics, where Boltzmann in particular made major contributions. By interpreting internal energy as the kinetic energy of molecules, it is explained why internal energy can be converted to mechanical energy. Entropy can be interpreted as the probability of a certain configuration of randomly moving molecules. Spontaneous increase in entropy is explained by the idea that randomly moving molecules spontaneously evolve to statistically more likely states. Having explained the relation between internal energy and mechanical energy, we still need to explain the relation with heat. The relation between kinetic energy and radiation is explained with radiation pressure. To explain why a black body at a certain temperature spontaneously emits radiation with a particular frequency distribution, Planck tried to invoke the principle of increasing entropy and apply it to the electromagnetic theory of radiation. To give a physical interpretation to the radiation law that he found eventually, Planck used Boltzmann's statistical interpretation of entropy. This interpretation involves the assumption that radiation energy comes in discrete chunks of energy. This is why Planck's radiation law will play a fundamental role in the development of quantum theory.
The following video from the YouTube channel Professor Dave Explains illustrates how the story of Planck's derivation is often presented inaccurately. While this simplified version may be acceptable for undergraduate education, it is unfortunately misleading for researchers seeking to develop new ideas.
Hey, it's Professor Dave. Let's talk about the ultraviolet catastrophe.
He knows a lot about the science stuff. Professor Dave Explains.
We know that the classical physics of Newton and pals reigned supreme for a few centuries. So what were the events that finally exposed its limitations? What was the first thing that suggested there was more to the universe than we had previously thought? This seismic shift was initiated in 1901 when Max Planck solved something called the ultraviolet catastrophe. The problem went like this. Certain objects are called blackbodies because they emit electromagnetic radiation of all wavelengths. The sun is an example of such an object, and we can take a look at the distribution of the wavelengths of light that we receive from the sun. Most of it is in the visible spectrum, which is why our eyesight evolved to pick up this kind of light. But we also receive light on either side in the UV portion as well as infrared and beyond. A hot piece of metal will also do this, and this was the way we studied blackbodies at the time, noting that the distribution depends not at all on the material, but only on temperature, with the particular wavelength that is emitted with maximum intensity shifting left as temperature increases. This maximum will move into the visible spectrum at around 4,000 Kelvin and above. This is why very hot objects appear to glow, like a hot oven, light bulb filament, or the sun and other stars, because objects at these temperatures emit a lot of visible light, as opposed to something like the human body, which at around 310 Kelvin emits essentially no visible light, which is why we can't see each other in the dark. The problem with the black body spectrum was that classical electromagnetism could not account for it. Mathematical models attempting to produce these distributions were able to fit the data for the longer wavelengths, but they did not predict that the intensity would dip down to the left for the UV portion of the spectrum, as experimental data illustrated. Instead, the math predicted that the intensity would continue to increase as the wavelength decreased and become infinitely large as the wavelength approached zero. Of course, we know that this can't be true. Otherwise, every time you use the oven, you would get blasted with UV radiation. This contradiction was dubbed somewhat dramatically the ultraviolet catastrophe. In science, if a theory does not accurately align with observations of reality, it must be revised. And so we realized that classical electromagnetism, as powerful as it is, must have some kind of limitations in its ability to describe light and energy. As we said, Max Planck solved this problem, and he did so by introducing a concept called quantization. We know from classical physics that heat is just the transfer of kinetic energy from one place to another. In the case of a piece of solid hot metal, that kinetic energy takes the form of atomic vibrations, or oscillations. These vibrations are what generate the light we see in the blackbody spectrum. Planck proposed that the vibrational energies of these atoms, and by extension, the energies of the electromagnetic waves emitted by these atoms, must be quantized, meaning that rather than being able to take on any value from a continuous series, they can only possess specific, discrete values from a set of accepted values. In this way, he developed this expression for blackbody radiation, where energy is equal to n, which can be any integer, times h, a term we call Planck's constant, equal to 6.626 times 10 to the negative 34 joules seconds, times f, the frequency of radiation. The n value is what results in quantization, as it can only be an integer and not any fraction or decimal in between, meaning that the resulting energies will also comprise a set of allowed values, with anything in between being forbidden. This application of quantization and the accompanying Planck's constant were developed in ad hoc manner, meaning that they were simply proposed for practical purposes, but they allowed for the accurate prediction of the true distribution of blackbody radiation at all wavelengths, which meant that this constant was more than a mathematical fluke, but a clue as to the fundamental nature of reality. And the fact that Planck's constant is so incredibly small explains why the notion of quantization of energy had not cropped up before, because it shows that energy is quantized on such an incredibly small scale that the gradations between the allowed values are utterly minuscule, so as to appear non-existent to any measuring apparatus. Energy appears to be continuous to macroscopic beings, such as humans, but on the fundamental level, it is indeed quantized, even though this conclusion was so strange that most scientists of the time, including Planck, couldn't believe that it had actual concrete physical meaning. This was the first time that quantization had solved such a big problem in physics, but it wouldn't be the last. It was the first in a series of developments that would utterly transform the field of physics, and by extension, our perception of reality. While Planck's work solved one problem, it created another. Why is there quantization of energy?
This video from the YouTube channel Kathy Loves Physics adds a human dimension to the story. It highlights how both Planck and Einstein were reluctant to embrace the quantum idea and continued to search for ways to incorporate Planck's constant within the framework of classical physics, particularly in Maxwell's equations.
Planck became interested in using entropy to explain an experiment created by the same Gustav Kirchhoff 30 years before called blackbody radiation. Planck recalled, quote, "It was an odd jest of fate that the lack of interest in my colleagues in entropy now turned out to be an outright boon. While a host of outstanding physicists worked on the problem, nobody paid any attention to the method adopted by me." It took Planck 6 years, but in 1900, Planck triumphantly produced his results. Then a co-worker of Planck's gave him some disturbing news. At relatively low energies, the equation that Planck just derived from fundamental equations didn't work. And so Planck quickly made up a new equation, quote, "which as far as I can see at the moment, fits the observational data." Planck was happy his equation worked, but he was not happy that it didn't have any theoretical backing. So in a self-described act of desperation, he turned to Ludwig Boltzmann's method of looking at statistics with molecules and entropy. Previously, Planck rejected that because he didn't like treating energy as a law of probabilities, but he was out of options. However, Planck didn't think much about his equation where he put the energy of the light into little energy packets, or quantized them. Quantizing energy was to Planck, quote, "a purely formal assumption, and I didn't give it much thought." However, he did spend many years trying his best to weld the elementary quantum of action H somehow into the framework of classical theory. But in the face of all such attempts, this constant showed itself to be obdurate, which is a good word, but I'm not sure I'm pronouncing it correctly. Then, in March of 1905, Planck was the editor of Germany's major scientific publishing paper, and he got a paper from an unknown scientist named Albert Einstein. Einstein took Planck's formal assumption of light being composed of energy packets as being a profound statement about the nature of light, and used it to explain a variety of phenomena, including the photoelectric effect. Surprisingly, Planck was completely unimpressed with Einstein's development of his idea, although he let it be published. By August of 1909, Planck invited Einstein to give his first public talk. Planck was probably hoping Einstein would talk about relativity, but instead Einstein talked about quantum mechanics, once again pushing a theory of light that can be understood as a kind of fusion of the wave and particle theories. Years later, a member of the audience recalled that the talk went nowhere, as the chairman of the meeting was Planck, and he immediately said it was very interesting, but he didn't quite agree with it. A few months after Einstein's first talk, tragedy hit the Planck household. Planck's wife of 23 years, Marie Planck, died from tuberculosis. Max Planck buried his wife and told his cousin that her grave is where, quote, my lost happiness is sleeping. Planck was 51 years old. His oldest son was 21, the twins were 20, and his youngest was just 16 years old. His relationship got much closer to his family, especially his youngest, Erwin. Back in 1906, a German scientist named Walther Nernst came up with an astonishing idea while trying to create nitrogen-based fertilizer. Nernst decided that two chemistry terms became identical asymptotically at absolute zero, which seemed to imply that the entropy would also asymptotically go to zero at absolute zero temperature, although Nernst hated talking about entropy. Within months, this theorem was being referred to as the third law of thermodynamics. Planck became the first theoretician to support Nernst in his theories, and also in 1910 became the person to figure out that the idea that entropy goes to zero was not true if the item was a compound or made of more than one substance. This rewrote the third law to be, quote, the entropy of a pure solid or pure liquid approaches zero at 0 Kelvin. A few years later, Nernst created his own final version of the third law to be, quote, it is impossible to cool an object to absolute zero. Scientists to this very day are still arguing about the proper form of this law. Anyway, in the spring of 1910, Nernst read Einstein's 1907 paper about using quantum mechanics to study solids and realized it could be used as a theoretical validation of his heat theorem. And within weeks, Nernst started talking with a wealthy soda magnate named Ernst Solvay about creating a conference on quantum issues starring Einstein. Nernst then immediately sent a letter to Max Planck detailing the whole plan. Planck was a little skeptical that the timing was right, writing that, quote, such a conference will be more successful if you wait until more factual material is available. However, Planck added that, whatever is done in this regard, I shall take the greatest interest, because I can say without exaggeration that for 10 years, nothing in physics without a break has absorbed, excited, and attracted me as these quanta of action. Nernst ignored the request to delay and personally set up the first international science meeting, called the Solvay Conference, beginning in October of 1911. Neither Planck nor Nernst knew that Einstein was less excited about the conference than Planck was. See, he had been trying to meld Planck's quanta of action, H, into Maxwell's equations with no luck. But Planck and Nernst were too famous to refuse, so he put together what he told his friend was some twaddle for the conference. Einstein thought the conference was a disaster, but the rest of the attendees were fascinated.
In 1954, just 1 year before his death, Einstein said in a letter to his friend Michel Bessot, all these 50 years of conscious brooding have brought me no closer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. In 1961, Louis de Broglie, the originator of the wave-particle duality concept for the electron, expressed serious criticism of quantum theory later in his life.
Je me trouve donc aujourd'hui dans une assez curieuse position. J'ai été, il y a près de 40 ans, l'un des initiateurs de la mécanique ondulatoire et de la physique quantique contemporaine. Obligations diverses, il devient presque impossible de conserver le temps et les forces nécessaires pour poursuivre avec continuité les travaux personnels difficiles. J'ai vu, non sans quelques surprises, le succès extrêmement rapide de mes conceptions, leur éclatante vérification expérimentale et les prodigieux prolongements qu'elles ont eus dans des domaines très divers. Et cependant, je ne suis pas satisfait. Au printemps de ma vie, j'ai été obsédé par le problème des quantas et de la coexistence des ondes et des corpuscules dans le monde microphysique. J'avais fait des efforts décisifs, mais cependant incomplets pour en trouver la solution. Aujourd'hui, à l'automne de mon existence, le même problème me préoccupe toujours. Car malgré tant de succès remportés et tant de chemins parcourus, je ne crois pas que l'énigme ait été vraiment résolue. L'avenir, un avenir que je ne verrai sans doute pas moi-même, tranchera peut-être la question. Il dira, si mon point de vue actuel est l'erreur d'un homme déjà assez âgé, qui reste attaché aux idées de sa jeunesse, ou au contraire, s'il traduit la clairvoyance d'un chercheur qui a réfléchi pendant toute sa vie sur le problème le plus fondamental de la physique contemporaine.
What if we could derive Planck's law differently? Let's explore a new method. We assume that radiation can be fully described by Maxwell's electromagnetic waves. Therefore, the concept of photons is not required. It's well known that electromagnetic fields carry momentum, and remarkably, that momentum can be expressed as the electromagnetic energy divided by the speed of light. In other words, the momentum of the field is E/em over c, where E/em is the energy stored in the field, and c is the speed of light in a vacuum. Let's suppose this electromagnetic wave transfers its momentum to an electron, setting it in motion with speed v. We start with the fact that the momentum of the electromagnetic field is given by P equals E/em divided by c, where E/em is the energy of the electromagnetic wave and c is the speed of light. If all this momentum is transferred to the electron, we can equate it to the electron's momentum. E/em over c equals m times v, where m is the mass of the electron and v its final speed. Now let's apply energy conservation. If all the electromagnetic energy goes into the electron, then E/em equals E electron. Substituting from our earlier momentum equation, E/em equals mvc. So we conclude, the energy gained by the electron is mvc. In a recent paper, we have shown something remarkable. It is possible to replicate the results of Compton's scattering experiment, not using quantum mechanics, but by solving Maxwell's equations numerically with a moving scattering particle. And here's the key insight. If the particle's speed is given by the formula v, divided by c equals lambda c over lambda plus lambda c, where lambda c is the Compton wavelength and lambda is the wavelength of the incoming wave, then the simulation reproduces the same wavelength shift observed in Compton scattering. In other words, classical electromagnetism, when done right, can capture an effect long thought to be exclusively quantum. We suppose that this velocity formula, originally derived in the context of the Compton experiment, can also describe blackbody radiation. Specifically, it can describe the frequency of the radiation emitted when an electron strikes the inner wall of the cavity. For blackbody radiation, we can simplify the expression for the speed of the electron. In this case, the wavelength lambda of the radiation is much larger than the Compton wavelength lambda c. So, in the formula v over c equals lambda c divided by lambda plus lambda c, we can neglect lambda c in the denominator compared to lambda. This gives a simplified relation, v equals lambda c times f, where f is the frequency of the electromagnetic wave, since c equals lambda times f. So the electron's speed is directly proportional to the frequency of the radiation. Earlier, we derived that the energy associated with an electron, when interacting with the electromagnetic field, is proportional to its velocity. Specifically, epsilon of v equals m times c times v, where m is the electron's mass, v is its speed, and c is the speed of light. Now let's think of a blackbody as a cavity filled with electrons. These electrons are indistinguishable, we can't tell one from another, and they are completely free to move around, bouncing off the walls of the cavity. Their velocities are continuous, meaning they're not limited to fixed values, and as they collide with the cavity walls and accelerate, they emit radiation, which is central to the blackbody radiation process. Our goal here is to determine the equilibrium distribution, n of v. That is, how many electrons occupy each velocity state v. We'll use classical statistical mechanics to find out what this distribution looks like under these assumptions. Inspired by Planck's original reasoning, but this time applied to velocity instead of energy, We now consider a system of indistinguishable particles distributed across different velocity states. We define two key quantities. First, n of v times dv. This represents the number of electrons with velocities between v and v plus dv. And second, g of v times dv. This gives the number of available states in that same velocity range. Since we're dealing with indistinguishable particles and no exclusion principle, we use Bose-Einstein-like statistics. The number of ways to distribute n of v electrons among g of v available velocity states, that is, the number of microstates, is given by this expression. Omega of v equals the factorial of n plus g minus 1 divided by the product of n factorial and the factorial of g minus 1. To simplify this, we apply Stirling's approximation, which is valid for large numbers, and we get log of omega of v is approximately n plus g times the log of n plus g minus n log n minus g log g. To find the total entropy, we integrate over all velocities. At each velocity, the contribution to entropy is proportional to the logarithm of the number of microstates, omega of v. So, the total entropy is the integral of log omega of v, multiplied by Boltzmann's constant. Next, we want to find the most probable distribution by maximizing entropy. But we have to respect two constraints. First, the total number of electrons must remain fixed. Second, the total energy of the system must also stay constant. To do this, we introduce a functional, a mathematical expression we want to maximize. It includes the entropy minus two terms, one enforcing particle conservation and the other enforcing energy conservation. These terms are weighted by Lagrange multipliers alpha and beta. This approach ensures that our solution is both statistically most likely and physically valid. To find the distribution that maximizes entropy, we take the variation of our functional. Setting the derivative with respect to the distribution equal to 0 gives us the condition for maximum entropy. From the entropy expression, we calculate the derivative of entropy with respect to the number of electrons at each velocity. This leads to a logarithmic equation that relates the available and occupied states. By rearranging the terms, we get a simple expression showing how the ratio of available to occupied states depends on the energy and the Lagrange multipliers. Now we solve for the distribution function, n of v. Starting from our previous result, we isolate n of v and express it in terms of the available states, g of v, and an exponential factor that includes energy. We substitute the expression for energy as mcv and redefine the constants. Alpha over k becomes the chemical potential mu, and beta over k is 1 over temperature. In thermal equilibrium, for freely radiating and indistinguishable particles, the chemical potential is approximately 0. That simplifies our expression to a familiar Bose-Einstein-like form, where n of v depends only on the available states, velocity, mass, and temperature. To calculate the spectral energy density as a function of frequency, we combine three key elements. First, the density of electromagnetic modes per unit volume and frequency, which grows with the square of the frequency. Second, the average energy of each mode, which we previously found to be proportional to the frequency with the constant mc lambda c. And third, the mean occupation number at thermal equilibrium, which follows the Bose-Einstein-like distribution we derived earlier. Multiplying these three components will give us the spectral energy density U of F, the amount of energy per frequency per volume inside the cavity. This result is identical in form to Planck's law, but arises without invoking quantized energy levels. To conclude, we'll now look at a simulation based on Maxwell's equations. It shows many electromagnetic sources with frequencies distributed statistically, so the radiation spectrum statistically matches Planck's law. This segment is accompanied by the music, Signal to Noise, by Scott Buckley.